All right, so this is a review of the Kahoot quiz. This first question says, a ball moves in uniform circular motion counterclockwise. What's the direction of the net acceleration, net force, and the velocity? As we know, the net acceleration and net force are what we call the centripetal force and the centripetal acceleration. Those will both follow path B inward. But the velocity, if the object's moving counterclockwise, is going to follow path C. Okay, so if you need to pause the video, these are 4 of the learning objectives that I'm going to be focusing on as far as the multiple choice test. Here are 5 more learning objectives. So again, pause the video if you want to read those. The first learning objective basically focuses on the idea of the force due to gravity. And in this particular question, what I was after, Mr. Morrison and Christian Clarence say that I didn't do a good job of making this clear, but let me try to do that. On part A, where the question is basically asking us what equation would we use for the force due to gravity when it comes to an object moving without any air resistance. Okay, and the answer there is we would use mg, the force due to gravity. For object B, the question asks, because of air resistance, the choice says because of air resistance, the object falls at constant velocity. Well, it's still going to be mass times gravity because gravity still works on that object. C says the object is thrown upward and is at the top of its path. So even at the top of its path, it's still going to experience a force due to gravity. So in all 3 situations, A, B, and C, all 3 objects are going to experience the same force due to gravity. One way of thinking about it is in the force toolkit, we always draw the force due to gravity as long as we're near the surface of the Earth. All right, so in this particular question, I'm not really 100% sure with what any other way that this can be asked on the AP test. Other than you're basically just putting this in your calculator. So the way we calculate the gravitational field near any planet is this. A big G, the universal gravitational constant, times the mass of the planet, divided by the radius of the planet squared. So for these values, it would be 6.67 times 10 to the minus 11th is the value of big G. We would multiply that times the mass of this planet, which is 1 times 10 to the 22nd, and divide it by the radius of this planet, which is 1 times 10 to the 5th. All we're doing is plugging into that equation, and our answer comes out as C. Okay, in this particular problem, we're going to look at this relationship here. If you look on your equation sheet, this equation is towards the bottom. It's the universal gravitational force. It tells us that the force between any 2 objects is the universal gravitational constant divided by the mass, multiplied by the mass of each planet and divided by the distance between them squared. So if we take the m part out of this, it becomes acceleration due to gravity. So on Earth, if we took the universal gravitational constant, multiplied it times the mass of the Earth, and divided by the radius of the Earth, we would get approximately the value 10 meters per second squared or 9.8 meters per second squared. So we could use that equation to solve this problem. It says the mass of a planet X is 1/10 that of the Earth and its diameter is 1/2 that of the Earth. What would the acceleration be at the surface of planet X? And the answer comes out to be 4. And so here's the solution to it. So on this new planet, the new planet's equation as far as its gravitational field would be big G, big M of the planet X, okay, divided by planet X's radius squared. Well, we're saying that planet X compared to planet Earth is 1/10 the mass. The problem says that the diameter is 1/2, so the radius must be 1/2 that of the Earth. So we're going to square that. After doing a little bit of math with this equation, we find that that comes out to be 4/10 g times the mass of the Earth divided by the radius of the Earth squared. Well, we know this part of the equation is equal to approximately 10 meters per second squared. More specifically, it's 9.8 meters per second squared. So if we take that value and multiply it times 4/10, we get approximately 4 meters per second squared. Okay, so let's derive the relationship between the velocity and radius of a satellite in a circular orbit. So this is something you have to be able to do, is to set the force due to gravity of an object in circular motion orbiting a planet as the universal gravitational force equal to the centripetal force. So mv squared over r equals big G mm over r squared. Doing a little bit of algebra there, we eventually find out that we get the relationship rv squared is equal to big G big M. Because these two are constants, we can say that for any radius r1, there will be a very specific velocity, v1 squared. That would equal some value gm, which would be a constant on any particular planet. Now, since that constant is going to be the same, if I were to change the radius to some value r2, then I would get a new velocity v2. And what determines those values are the other three values. So, for example, to solve for r2, I would need to have r1, v1, and v2, and I would solve that algebraically. This next question, however, focuses more on that equation right there. RV squared is equal to GM. This question says a satellite mass m and speed v moves in a stable circular orbit around a planet of mass m. What is the radius of the satellite's planet? So going back to our derivation, if we follow it all the way to this part of it and solve it for r, we get big G big M over v squared. So the answer in this case was C. Okay. Boat rates question, we don't need to know about that. Okay, so remember in calculating the torque, so let's say we have a certain distance r and we apply a force at this location. Remember, the only component of the force that's necessary is this vertical component. Think of it this way. What component of the force will make this object spin? And only that component of it will, not this parallel component. So it's the perpendicular component of the force causes the torque. So we take that perpendicular component, F, and we multiply it times R. Okay, so in this particular question, it says different weights are hung from a pulley that is made out of a solid disc. A special instrument is used that can measure the torque applied to the pulley. A rough sketch of the graph that results from measurements of the torques and weights is known. If the best fit line is drawn to find the slope, it would represent what? And it turns out that in this particular graph, if I look at this as y equals mx plus b graph, I would set my y equals mx plus b equation over here as this would be my y, this would be my x. So notice the force due to gravity here, the weight is the horizontal variable. The torque is a vertical variable. So if this is a y equals mx plus b equation, my slope would be the radius. Okay, so r would be the radius. That would be part B. So again, think of this as y equals m, the slope, times x in our y equals mx plus b equation. Okay, now we want to compare the torques of each of these objects. So the torques, the torques on this beam, if you will, from these forces. Okay, so there are actually 5 forces here. There's a normal force up there, but it's not producing a torque because that force is right at the center of mass. Okay, about its axis of revolution. So its R would be 0. This mass produces a torque that is the mass times 9.8 times 2. That would be, for this one, object X, 2 times 9.8 times 1. This is 1 times 0.5 times 9.8. And this is 1 times 9.8 times 2. So the torque with the greatest magnitude would be W. Okay, 2 times 9.8. X and Z would be the same. They're both 2 times 1 times 9.8. 2 times 1 times 9.8. And Y would have the smallest magnitude because it's 1 times 0.5 times 9.8. So the correct answer there is 8. Okay. So we got 3 objects. We want to find the net torque. Basically, we can look at the rotational inertia on each. So object 3's rotational inertia is mr squared. So it's got the highest torque. So T3. Then next would be 2/3 mr squared, which would be this T2. And finally, the first one, 2/5 mr squared. So the correct answer there is B. Okay, in this question, we want to figure out which of these 3 forces is going to balance out this force here, F. Notice this force F here is 3 squares long, if you will, in the vertical. Remember, only the perpendicular matters. And we've got 3 perpendicular units of force there. Over here, 2 couldn't be the correct answer because it's got 4 perpendicular units of force in the vertical. 1 has 3 vertical units of force, so that will on its own balance out F, and so will 3, because 3 has 3 vertical components of force. So 1 and 3 both will each be enough to balance out this force F, because they each have 3 vertical components of force. All right, in this particular question, we want to solve for the solid disk. So we just plug that into mr squared, 1/2 mr squared. So we would take this mass 4 and this radius 0.5, the entire radius, plug it into that equation to find the rotational inertia. And I believe that comes out as 0.5 kilogram meters per second squared. Then it asks, so that's the rotational inertia. Then it asks for the net torque on the disk. So what we do there is we take, the torque equation is the force times R. So this torque, let's call it T1, is going to be 4 times 0.5. So that's going to be 2. And because that's going to make it spin in a counterclockwise direction, that's going to be a positive 2 Newton meters of torque. The other torque, T2, is going to make it spin clockwise, so let's call that negative. So that's 4 times 0.25, which would give us -1. So 2 and -1 gives us a total net torque of 1 Newton meter. The next question asks for the angular acceleration. So to solve for the angular acceleration, we know the net torque is equal to the rotational inertia times the angular acceleration. So we take the net torque, which we solved for previously, which was 1, and divide it by the rotational inertia, which was 0.5, and we get an answer of 2 as the angular acceleration. Okay, then to find the angular velocity after 2 seconds, we use one of our, we would use a kinematic strategy, omega equals omega initial plus omega t. Alpha t. So let me say that again. Omega equals omega initial plus alpha t. The alpha we know, we already calculated earlier, was 2. So 2 times 2 would give us 4 radians per second. Okay. And if I misspoke earlier, the acceleration for the previous question should have been in radians per second squared. All right, and that's it.